Assalamualaikum and how are you guys? Let's continue our topic material balance on a single phase, whereby we're going to learn about real gas and ideal gas. Last time when we learned science, we learned about phases, solid, liquid and gas. And we learned about the property of the material, which is a density and a volume. Here, I would like to introduce to you the term incompressible and compressible. I believe you already know about this. For solid and liquid, it is incompressible because the change of a temperature doesn't have any effect on the density. However, same goes with the change of pressure. However, for gas, the volume and the density are really affected by the pressure and temperature. Okay? For a gas, the density, the volume are really affected by temperature and pressure. Before we proceed with a detailed topic about gases, I would like to introduce to you a book, Paris Chemical Engineer Handbook, which is this book. Okay, this is 8th edition. The latest edition should be 9 or higher. This book contains a lot of property data for almost all the chemical. Later on, this book is really useful for you when you do your plant design project. And I would like to recap to you these two formulas for you to calculate a density, especially when you have a mixture. You can use this one or this one, whereby the density and the mass fraction and the total density, basically a mass fraction time the density of each of the species in that mixture. I believe we learned about this before, right? Okay, let us come back to the property of the solid, liquid and gas. Let's say I have two temperature and pressure, T1, T2, P1 and P2, which is two different temperature and two different pressure. What happened to the density and a volume of a solid and liquid is remain the same. Okay, it's remain the same. However, for a gas at P1 and T1, the density is equal to ρ1 and a volume is a volume 1. What happened when the change of a temperature and the change of pressure occur, which is at P2 and T2, the density of a gas and a volume of gas is changing based on the temperature and pressure. Because of this, we need a relationship of PVT. We need a relationship how to relate the density, how to relate a volume with a pressure and with a temperature. Therefore, when we have a volume, a temperature and a pressure, we would like to relate it into a single equation we call PVT relation. And the equation is named as ideal gas equation of state. Since this is the first time you heard about this, I would like to introduce to you PV equal to nRT, which is ideal gas equation of state. So this equation will relate the molar quantity, volume of gas to a temperature and pressure. And it also can be written in this form. I believe you already noticed that the symbol dot here is the flow rate, right? Okay, so P is the absolute gas pressure, V is a volume or volumetric flow rate of the gas, N is the number of mole, R is a gas constant, whose value depend on the unit of pressure, volume, mole and temperature. Depend on the unit. Okay, it have a numbers of gas constant. This R is depend on the unit, and each of the unit give a different values. Okay, and T is the temperature. Note that the ideal gas equation of state is only an approximation. So, because of this is an approximation, it tends to be an error. So, people decide how to determine the error. It's just basically when we have the value of either P, T temperature, all this value, it could be pressure, temperature, a mole and a volume. We just find the difference between the ideal and the true values, and we can get how much the percentage of error. Then it's good to have the error less than 1%. So in order to calculate the error, one of the method is to calculate the ideal specific molar volume, which is this one. Okay. And then if it is more than 5 liter per mole for diatomic gas, then it will be okay. If the value is higher than 20, for other gas, it also consider the error is less than %. Okay, don't worry so much about, I might not giving you long and lengthy explanation, because in this topic, I would like to simplify for you that there are an equation that relate pressure, volume and temperature, which is called the ideal gas equation of state. And the equation is this one, PV equal to nRT. And you going to use it, just apply it. Okay, you don't need to take care on how to derive it. So don't worry. Okay, don't worry so much. Okay, just remember PV equal to nRT, P for pressure, V for volume, N is a mole, R is a gas constant, and T is a temperature. You know, let's go to an example on how we're going to use this PV equal to nRT. This time, I try my best to put a lot of example for you. Okay, when we have this example, 100 gram of a nitrogen is stored in a container at 23 degrees C and 3 psig. First one, assume it is an ideal gas behavior and calculate the container volume in liter. Okay, we need to calculate the value of V. Okay, because it states that the question states that assuming ideal gas behavior, meaning to say this equation want us to use PV equal to nRT. And the second one, we have to verify whether this is a good approximation or not, which is for us to calculate the error. Let's see the solution. Okay, so assuming ideal gas using PV equal to nRT, and we rearrange this equation so that we get a volume, because we want to find a volume. So we rearrange this equation, make a volume become a factor. Okay, and we have to find the number of mole, because it's given here 100 gram, okay, which is a mass, and we already know what is the molecular weight of a nitrogen, so we can find the mole of a nitrogen here. Okay, and then the next one, we have to be careful on the temperature, the unit of the temperature. Okay, so we use a Kelvin, so we need to convert from a degree C into a Kelvin, and then we can find the volume, which is using PV. Using this equation, we can find the volume. We just substitute what is the value of N, what is the value of T, what is the value of R, and don't forget that you have to do a unit conversion here, which is from PSI to ATM. 1 atm is equal to 14.7 psi. Okay. So we get the value of volume is 72 liter. Okay. And then we have to verify whether it is a good approximation or not, which is by calculating the error. So we can straight away using that formula, which is we are calculating using, because we don't know the true value. Okay. Remember last time the formula, okay, the formula, which is you have to find the difference between an ideal and the true one. Okay, but here we don't have the true value, so we can use another alternative, which is we calculate the volumetric flow rate. Sorry, we calculate the volume, the molar volumetric. Okay, which is this one. So it is more than 5. Okay, we get the value about 20.2, which is more than 5 liter per mole, and nitrogen is an diatomic gases. So this approximation is a good approximation because the value of error is less than 1. Okay. So this is a really simple example for you to understand how to use this PV equal to nRT. I really hope that this example are really I really hope that you can understand how to use PV equal to nRT. This is example number 1. There's a lot of example later on. Okay. So this ideal gas equation of state PV nRT, it also have alternative form, in which when we do calculate a specific molar volume, okay, specific molar volume, this one, so we can change it into this PV equal to RT, because the V divided by N, we get this V. And another alternative form, we can relate this with a density. Okay, because a volume, a molar volume, is a mass over density. Remember the formula of density, which is a mass over volume, right? So we just interchange the position. We get the mass over density is a volume. Then from there we can get the equation if we want to relate the density to a temperature and a pressure, and we can use this equation. Early in the video, I did mention about a density, which is a rho, and a volume. Okay, so these two can be related to a pressure and a temperature based on equation of state PV equal to nRT for this one, and for the volume you can relate by PV equal to nRT. For the density you can relate by using this equation. Okay, then what about the gas constant, which is the value of R? Okay, the value of R, there are a few number. The gas constant. How about the gas constant? The gas constant really depend on a unit. As you can see here, each of it having a different unit, whether the unit of volume in liter or meter cube, the unit of pressure bar, Pascal, atm, psi, and same goes with the unit of a temperature and a mole. Okay, so you have to choose properly which of the unit suitable for you based on the unit of a temperature, unit of pressure and the unit of mole together with the volume. Okay, so choose properly. Okay, let us continue. Okay, a standard temperature and pressure. This is an alternative if you don't want to use a gas constant. If you don't use gas constant, or you cannot memorize, and or you choose not to memorize the value, we have here an alternative, which is a standard temperature and pressure. Standard temperature and pressure, whereby we have equation of state at standard temperature and a standard pressure. At standard P and standard T, we have this equation, and when we are combining these two equations with a general equation for ideal gas equation of state, we can get another equation because we cancel out the value of R. Therefore, we can use this equation. But you still have to memorize one value, which is the value of, okay, you don't need R here because it cancel each other. Okay, but you still need to memorize another value, which is the value of standard molar volume, which is this one. Okay, and it's the same for these two units, but different for another unit. Okay, and these are the value of it is a standard condition. Okay, molar volume is this one, and the value of a temperature, standard temperature and standard pressure, as you can see in this figure, which is for a standard pressure, it is 1 atm, and for a standard temperature, it is 273 Kelvin or 0 degrees C. Okay, and this is the mole, everything. So this is another unit. Some people not written this molar volume as this unit. They will just write it as a SCM, which is a standard cubic meter cube. Sorry, it is a standard cubic meter. Standard cubic meter meaning to say it is in meter cube. And people also write it as a SCF, which is the unit is a feet cube. Okay, feet cube. Okay. So let's say you have 18.2 SCMH, meaning to say standard cubic meter per hour. Okay, meaning to say the unit is meter cube at at temperature 0 degrees C and 1 atm pressure. Okay, I might not arrange my sentence properly, but don't get confused with this. Okay, so if you don't remember the value of R, there is still an alternative for you to use this equation of state, but you have to remember the value of molar volume, which is this one. Okay, 22.4 or 359. It's easier to memorize as compared to the value of R. It's a lot, right? And this also telling you about, this is just a notation, a symbol, which is people want to say when you have standard cubic meter, SCM is actually a meter cube, and when you have standard cubic feet, is actually feet cube. Don't get confused and don't bother so much about this. Okay, let us go to another example on how we can use this standard temperature and pressure equation. Okay, so here the example number 2. Okay, when we have a butane at temperature 360 degrees C, 3 atm, and it flows at, this is mass flow rate. Okay, and then you have to calculate the volumetric flow rate. Okay, volumetric flow rate by using a standard condition. Okay, meaning to say this equation wants you to use this equation instead of PV equal to nRT. Okay, so again, what you need to do, you just need to rearrange, because you want to have a, you want to find a volume. So rearrange this equation so you get this equation. Okay, yes, I said that you want to find, although you might don't want to find it. You might say, madam, I don't want, you want it. Okay, that's all. Okay, so the next thing to do is you can calculate the mole, which is the value of mass over molecular weight. So you can get the value of mole, the N. Okay. And then the next thing is you have to do a unit conversion of your temperature. Okay, it is in a Kelvin. Always, if I'm not mistaken, they always use a Kelvin. They always use a unit Kelvin throughout this topic. Okay, so you just bear in mind that change all the unit to Kelvin, and then you have the value of N, you have the value of standard volume 22.4, you have a temperature, this one, and you have a standard, which is 1 atm. You have a standard temperature, which is 273K, and then you have a P, which is 3 atm. Don't forget to convert it. Oh, no need to convert it. 3 atm. You can cancel out each other, so you can calculate the volume. Okay, once you calculate the volume, you get the value of 329 meter cube per hour. Okay, try to calculate it. If there is an error, don't blame me, because I just took everything from the reference book and I don't press my calculator. Okay, you can press it by yourself. Okay, the next is another example. I believe you really like example so much, so let's move on to example 3. Okay, so we have a lot of example in this topic. Okay, let's see. Okay, you have a, what do we have here? Okay, we have a air. Okay, at this temperature, Fahrenheit, the unit is Fahrenheit, and then at this pressure is heated. Okay, so the pressure is increased. So we have T1 here, we have T2 here. Okay, so someone might asking me, why T1, why T2? It's just for me to show you have a different temperature. Okay, you can have a TA and TB. It doesn't matter. It's just for me to show that I have two different temperature. And also, I put it P1 and P2 here, which is I have a different pressure. And what happened here is compress and heater. Okay. Heater is to increase the temperature. Okay, heater is used to increase the temperature. Compress, which is a compressor, and equipment used to increase the pressure. Okay, as an engineering technologist, you have to familiar with this equipment. Okay, what are the volume of gas in a final state? Okay, we have two volume, right? Because the volume of gas is really affected by temperature and pressure. So the V1 is 10 cubic feet. Okay, 10 feet cube. Okay, 10 cubic feet. So why I'm saying 10 feet cube? Okay, it is not 10 feet cube, it is 10 cubic feet. Okay, sorry for that mispronounce. Okay, we have a compressor. Okay, we have a compressor. Okay, let me correct it. When you compress a gas from one pressure to another pressure, the temperature will be also increased, and you don't need another equipment called heater. Okay, it's enough for you to use compressor. Okay, so you have the condition 1, whereby V1, T1 and P1, okay, and then compress into another temperature, another pressure, sorry, but when we compress, the temperature will be increased too. Okay, so because of these just two conditions, we can just use PV equal to nRT. Just put it 2, okay, PV equal to nRT for condition 1 and condition 2, and we rearrange so that we can cancel the value of R, we can cancel the value of mole, left only PVT relationship. Okay, what we want to find is the V2, right? So we already have T1, T2, V1, P1, P2. So we can calculate the value of V2. Okay, don't blame me because keep on cycling this. Okay. So you can calculate the value of V. We just rearrange. This is mathematics. Okay, just rearrange the equation, and then you can get. Don't notice that it is a unit of feet. Okay, and they use Rankine, another unit of temperature. I know that you are not so familiar with this unit. Me either, but it's okay. We just use it. So we can get the value of second volume. Okay, a final state volume, which is cubic feet. Okay, cubic feet, not feet cube, cubic feet. Okay.